welcome. Um, as you just sort of settle into your chair today, I want you to take a slow, really deep breath.
Just let the noise of the day kind of, gently fade away.
Exactly. And I want you to imagine, just for a moment, a kidnapper sitting quietly in this dimly lit, silent room.
A very calm, deliberate scene.
Right. And they aren't writing a ransom note with a pen. Instead, they're painstakingly, methodically cutting individual letters out of a magazine.
Just preparing to paste them together into a new, completely unintended message.
Yeah, and today we're going to explore this tranquil, distraction-free space with you to understand how modern hackers do the exact same thing to our computers.
It's really a beautiful, if malicious, art form.
It really is. Our mission today is a deep dive into one of the most intricate, elegant, and notorious techniques in all of computer science.
Which is return-oriented programming, or ROP.
ROP. We're going to learn how attackers harvest the computer's own, digital letters to write their malicious instructions.
Using the system's own weight against it.
Right. So as we spend this time together decoding the dark channel of system memory, I'd like to softly invite you to leave a like and subscribe if you enjoy this soothing exploration of complex topics.
So that metaphor of the ransom note.
Yeah.
It was actually originally introduced by the brilliant cybersecurity researcher Hovav Chacham.
Oh, really? It perfectly captures the vibe.
It truly does. It captures the essence of the landscape we're about to explore. But, to appreciate the sheer ingenuity of cutting digital letters out of a magazine, we first have to understand the environment.
Right. Like, what forced an attacker into such a meticulous, painstaking method in the first place?
Exactly. We need to look at how a computer fundamentally views the programs it runs and the historical arms race that brought us here.
Okay, let's unpack this, because I'm trying to visualize the environment before this ransom note technique even existed.
It was a very different world.
I assume attackers didn't always have to go through the trouble of scavenging for individual letters, right?
No. There was a time when things were much, much more straightforward, where they could just write whatever they wanted.
I mean, that sounds almost too easy.
The environment used to be remarkably trusting. In the golden age of software exploitation, the attacks were incredibly direct.
So paint a picture of that for me, and for you listening.
Sure. Let's visualize a program's memory. When you, say, double-click an application on your computer, the operating system allocates a vast, empty canvas of memory for that program to use.
Just a giant blank space.
Right. And this memory is divided into different sections. One of the most critical sections is this thing called the stack.
And the stack is essentially, well, the program's short-term memory, right? Like a place to jot things down quickly.
That is a really helpful way to visualize it. The stack operates exactly like a physical stack of plates in a cafeteria.
Oh, okay.
When the program needs to remember a small piece of information temporarily, say, your name or a local variable or just the result of a quick calculation.
It pushes a new plate onto the top of the stack.
Exactly. And when it's done with that information, it just pops the plate off. But the stack also holds something of paramount importance.
Which is?
The saved return address.
Okay, wait. I want to make sure I, and you listening, truly grasp this concept of a return address, because it seems central to, well, everything we're going to discuss today.
It really is the key to the whole castle.
If a program is just running, why does it need to save an address?
Well, programs are built out of functions. Small, self-contained blocks of code that do one specific job.
Like a specialized worker.
Right. So if the main program needs to calculate the square root of a number, it jumps over to the square root function.
Makes sense.
But once that function finishes its math, the processor needs to know exactly where to go back to in the main program to continue its work.
Ah, I see. So before making the jump to the new function, the program writes down its current location on a piece of paper, like a little breadcrumb, and leaves it on the stack.
It pushes that breadcrumb onto the very top of the stack, then it jumps.
And
when the function finishes, the processor mechanically looks at the top of the stack, reads that breadcrumb, and returns home.
wow, it's so elegant, but I can already see how fragile it is.
It's extremely fragile. This delicate system of trust created a monumental vulnerability. It led to a technique known as stack smashing.
Stack smashing, which is a form of a buffer overflow, right?
Yes, exactly.
Let's walk through that slowly. What exactly is overflowing in a buffer overflow?
So imagine the program asks you to input your username, and it sets aside a small space on the stack, a buffer, that's designed to hold, let's say, exactly 50 characters.
Okay, 50 plates on the stack.
In the early days, many programs would simply take whatever you typed and start copying it into that space on the stack, byte by byte.
Just blindly trusting you.
Entirely, without ever checking if it was too long.
Oh, wow. So if I type a username that is like 10,000 characters long, the program just keeps writing.
It just keeps writing.
Yeah.
It blindly fills up the 50-character buffer and just keeps spilling over into the adjacent memory space on the stack.
And that adjacent memory space,
Yeah.
that's where the breadcrumb is.
Exactly. That space contains that critical breadcrumb, the saved return address. So the attacker carefully crafts their oversized username so that at the exact moment, the program is overwriting the save its return address.
The attacker provides a new forged address.
You got it. They overwrite the breadcrumb with a fake map.
That is so deeply clever and so simple.
It is. But furthermore, tucked away at the very end of that massive 10,000 character username, the attacker includes their own malicious machine code.
The actual payload.
Right, often called shell code. So they overwrite the return address with a pointer that points directly to their own injected shellcode sitting further down the stack.
Wait, let me picture this. When the function finishes, it reads the forged breadcrumb, assumes it's heading home, and instead blindly jumps directly into the attacker's weapon.
Yes, it just executes whatever the attacker left there.
I see the directness now. The attacker literally brought their own fully assembled weapon, placed it in the room, and tricked the computer into picking it up and firing it.
And the computer just obeyed.
Because it doesn't distinguish between the data I typed in and the instructions it's supposed to execute.
Data is code, and code is data.
That trust is almost tragic. But obviously, the companies building our hardware and software couldn't just allow anyone to inject weapons directly into memory forever.
No, they couldn't. The defenders of the digital realm responded with a sweeping fundamental change. They altered how memory is governed at the deepest levels of the hardware and the operating system.
What did they do?
Architects at companies like Intel, AMD, and Microsoft collaborated to introduce data execution prevention, or DEP. Okay? And this defense mechanism is governed by a beautifully simple, ironclad mathematical property. It's known as WX.
WX, right? XOR, execute.
Exactly.
The poetry of that mathematical logic is really appealing. For anyone listening who might not be familiar with logic gates, XOR stands for exclusive, or meaning one condition or the other can be true, but never both at the same time.
Applying that simple logic to computer memory fundamentally altered the entire landscape of cybersecurity.
I'm trying to picture this restriction. It feels like a very strict policy inside a grand, hushed library.
I like that. Let's build on that.
Let's say in this library there are reading rooms and there are writing rooms. The WX policy dictates that a single page in a notebook can either be written on, like a blank scratch pad, or it can be read aloud as official instructions, like a rule book. But it can never, ever be both at the same time.
That's a perfect visualization. Building on that, the stack, where our oversized username and injected shellcode are stored, that's the scratch pad.
Because the program needs to write to it constantly.
Right. The operating system explicitly marks the entire stack with the right permission, because the program constantly needs to push and pop those temporary plates of data.
Makes sense.
But under the WX policy, because the stack is writable, it is explicitly stripped of the execute permission.
Oh, so even if the attacker successfully overwrites the breadcrumb and forces the program to jump to the injected shellcode on the stack,
the processor will simply refuse to read it.
you can write your malicious thoughts in the notebook, but when you hand that notebook to the librarian and demand they read it aloud as the new rules of the librarian simply shakes their head.
Exactly. The environment physically prohibits it. The processor triggers a hardware-level exception, often resulting in a blue screen or a silent crash. But the malicious code never runs.
The weapon is confiscated at the door.
It is. And this brings us to the profound paradigm shift that gave birth to return-oriented programming.
This is where we transition from the direct attack to the ransom note.
Precisely.
So if the computer physically refuses to execute the attacker's injected code, how did attackers keep winning? If the WX policy says you absolutely cannot run injected code, how is the attacker making the computer do anything? Are they hacking the WX policy itself?
No, that's the genius of it. They're obeying the policy entirely.
Wait, really?
Yes. They realized that if they cannot bring their own weapons into the library, they must use the weapons that are already lying around the room. The original program, the system libraries, the very fabric of the operating system, all of these are loaded into memory. And out of absolute necessity, They are marked as executable.
They are the official books of the library.
Exactly. The computer has to be able to run its own code, otherwise it wouldn't be a computer.
Right, of course.
And that authorized executable code is massive. Modern programs don't operate in isolation. They dynamically link to massive libraries, such as the lib library in Linux or NTL in Windows.
And those libraries contain, what, everything?
Pretty much. They contain the instructions for everything a program might ever need to do. Print text to a screen, open a file on the hard drive, establish a network connection over the internet.
It's a vast ocean of pre-approved instructions.
Millions upon millions of bytes of executable code. So the attacker simply harvests fragments of this approved code and changes the order in which those fragments are executed.
They don't inject a single line of new kind.
Not one. They just orchestrate the existing code to perform a malicious symphony.
Wow. Which brings us into the microscopic mechanical reality of the computer's processor.
The lowest level.
We need to talk about the individual letters they cut out of this vast ocean of code. Because in this world, those letters are called gadgets.
Yes, gadgets. A gadget is a tiny pre-existing snippet of assembly instructions already living inside the target binary or those dynamically linked libraries.
How small is tiny?
Incredibly short, perhaps just 2 or 3 instructions long. It might do something exceedingly simple like moving a numerical value from one processor register to another, or doing a bit of basic addition.
Okay, for anyone listening who isn't a low-level software engineer, when we talk about processor registers, we're just talking about incredibly tiny, highly specific slots inside the CPU itself, right?
Right.
Where it holds numbers for just a fraction of a second while it works on them.
Right.
Like tiny hands holding puzzle pieces.
That is an excellent way to describe them. Registers are the absolute fastest form of storage in a computer, the physical workbench of the processor.
Okay.
So a gadget might take a puzzle piece from one hand and move it to the other. But crucially, in traditional return-oriented programming, every single one of these microscopic gadgets must end with a very specific instruction.
And what is that?
The RET, or return instruction.
Okay, and this is where the architecture of the machine reveals its hidden secrets. How do attackers actually find these gadgets? Surely the original programmers didn't intentionally write millions of tiny 2-line functions that all neatly end with a return.
What's fascinating here is that attackers often don't use the instructions the programmers intended to write at all.
Wait, what do you mean?
They exploit a quirk in the immensely popular x86 architecture. You know, the type of processor powering most desktop computers and servers.
Okay, what's the quirk?
On the x86 architecture, instructions are of variable length.
Variable length.
Yes. One instruction might be a single byte long, while the very next instruction might be 15 bytes long. Furthermore, they do not need to be aligned to specific memory boundaries.
I am trying to wrap my head around this. If I read a book, the words are clearly separated by spaces. I know where one word ends and the next begins. Are you saying the computer's memory doesn't have spaces between the instructions?
Exactly. The processor simply reads a stream of bytes, starting from wherever it is told to look.
Okay.
Let me paint a picture using English letters. Imagine a sentence written completely without spaces. That kitty is red.
The cat is red.
If you start reading from the very beginning, you parse the intended words. The E, cat is red. These are the legitimate instructions the programmer compiled.
But the computer doesn't know about the concept of words or intentions. It only knows the starting address.
Precisely. If an attacker forces the processor to start reading just one single letter to the right, starting at the H instead of the T, the text parsed by the processor becomes he, cat, is, RD. Suddenly, he is a completely valid word that was hidden inside the intended word, VHE.
That is wild, because the instructions in x86 are variable lengths and unaligned. Dropping the needle down just 1 millimeter off target plays a completely different song.
Exactly like dropping a needle on a record.
Yeah.
In the raw binary of a compiled program, the density of valid instructions is staggeringly high.
So they just look for the ends of these hidden words.
Yes. The byte that represents the red instruction in x86 assembly is simply the hexadecimal value C3.
C3.
Just that one byte. If a programmer writes a complex mathematical instruction, and one of the data values within that instruction happens to contain the byte C3.
Even if it was meant to be part of a number, not an instruction.
Exactly. Jumping to that specific byte halfway through the instruction will cause the processor to instantly execute a return.
It is like finding a hidden message in a painting by looking at it under a different spectrum of light. The gadgets are there, sleeping as ghosts in the binary, completely unknown to the developer who wrote the code.
Beautifully said. By scanning millions of bytes of libraries for the C3 byte and then reading backwards byte by byte, attackers discover thousands of these hidden gadgets.
Wow. So once they have their catalog of letters, they must arrange them into a ransom note.
They do.
And to understand how they force the computer to read that note, we need to talk about the conductor of this silent orchestra. Normally, a computer program is guided by a specific register called the instruction pointer.
The instruction pointer.
Right. I picture it acting like a spotlight, moving line by line down the page of code, illuminating one instruction after another, telling the CPU what to do next.
That's spot on. The instruction pointer, known as %APE in 32-bit systems or %REP in 64-bit systems, is the traditional, undisputed master of control flow.
Okay.
But in an ROP attack, the attacker dethrones the instruction pointer.
They overthrow it.
They do. Through their initial buffer overflow, they manage to promote a completely different register to act as the new program counter.
Which is?
The stack pointer, or %INSP.
This is a beautiful, terrifying inversion of control. The stack pointer usually just keeps track of the top plate in our cafeteria stack, our scratch pad.
Right, the temporary data.
But the attacker fills that scratch pad, the stack, with a long list of memory addresses.
Yes.
And each address points to a gadget scattered somewhere out in that vast ocean of the executable library.
That's it exactly. And the mechanism that makes this sequence flow, the beating heart of the entire exploit, is that read instruction at the end of every single gadget.
The C3 byte.
We must look very closely at what the read instruction literally does at the silicon level.
Walk us through it. The CPU hits the C3 byte. What happens physically inside the processor?
When the processor encounters a read instruction, it performs an automatic mechanical sequence. First, it looks at wherever the stack pointer is currently pointing. It picks up the data sitting right there on the top of the stack, which, in an ROP attack, is the memory address of the next gadget.
The next letter in the ransom note.
It pops that address off the stack, which automatically slides the stack pointer down to the next item.
Okay.
Finally, it forcefully jams that popped address into the instruction pointer, commanding the CPU to jump to that new location.
It is so incredibly mechanical, so blindly obedient.
Completely blind.
You know, I like to think of the read instruction as the carriage return lever on an old manual typewriter.
Oh, that's a brilliant analogy.
Clackdizing. The gadget executes its tiny operation, maybe it moved a puzzle piece from one hand to the other, and then the RET acts as the lever, physically sliding the processor's attention down the stack to the next address the attacker provided, pulling the next gadget into the machine.
That typewriter analogy perfectly captures the rhythm. The CPU has absolutely no idea it is executing a malicious, stitched-together chain.
It just thinks it's doing its job.
It believes it is just dutifully returning from a series of microscopic, highly fragmented functions. It is blind obedience, weaponized by the constraints of the architecture.
Amazing. So we have the typewriter carriage ready to pull our fragments one by one. But an attacker can't just type random letters. They have to spell out a specific, complex command to the operating system.
They do.
How do they actually string these tiny additions and subtractions together to do something meaningful, like completely taking over the computer?
That leads to a fundamental question of computer science. Are these scattered snippets enough to actually write a complex program?
Are they?
The answer, proven mathematically, is yes. If you gather enough distinct types of gadgets, a gadget to add, a gadget to subtract, a gadget to load a value from memory into a register, and a gadget to branch or make a decision,
You basically have all the building blocks.
you achieve a theoretical state called Turing completeness.
Turing completeness, a deeply soothing term named after the brilliant Alan Turing.
It is.
For our listeners, it essentially means that with this specific, finite set of broken fragments, you can program the computer to compute absolutely anything it is physically capable of computing. There are no limitations.
None. You have rebuilt a universal computer out of the shattered pieces of another.
That's just staggering to think about.
You have complete expressiveness. However, piecing them together by hand-searching through millions of bytes of raw machine code for the exact sequence of registers you need to manipulate would be an agonizing, nearly impossible task for a human being.
And trying to build a functioning watch out of sand by looking through a microscope.
Exactly. Which is why modern attackers and the security researchers who study them do not do this manually. They rely on elegant, automated tools.
The automation.
As we explore the sources provided for this deep dive, we see mentions of several vital utilities. Tools like ROP Gadget, ROPR, RP plus sed and mona.pi.
These are the attacker's specialized search engines.
They are.
How do they work? Do you just feed them the library file?
You point these tools at a compiled binary file, like a windows.exe or a linux.elf file. The tools systematically scan through the dense forest of assembly code, decoding the bytes, hunting for every single RET instruction.
And looking backwards, like we talked about.
Yes, mapping out the preceding instructions. They identify every possible gadget, categorize them by what they do to the registers, and map their exact memory addresses.
And they don't just find them, they curate them, because memory isn't always a clean blank slate. I was reading the notes about bad characters.
Yes, bad characters. The environment often imposes strict formatting constraints on the ransom note.
What kind of constraints?
If an attacker is injecting their long chain of addresses via a text input field on a website or a network protocol, they might not be able to use certain byte values. A classic example is the null byte.
Represented in hexadecimal as 0000.
Oh, right.
Why is 000 so dangerous to the attacker?
Well, in many foundational programming languages, particularly C and C++ ROD, a null byte is universally used to signal the end of a string of text. It is a hard stop sign.
Okay, so if it sees a null byte, it thinks the sentence is over.
Exactly. If your carefully constructed ROP chain contains an address that happens to have a null byte in it, say the address is 0000000 the program reading your input will hit that 00, think the input is completely finished, and simply stop reading.
Oh wow. The rest of the chain is cut short, completely ruining the exploit.
The carriage return stops pulling the paper.
So these tools automatically filter out any addresses containing bad characters, ensuring the chain is robust and unbroken.
That's right. It does the filtering for you.
To really ground this in reality, let's walk through a historical event. The sources detail an exploit developed by the Cosmos team at Bishop Fox and NCC Group for a vulnerability known as CVE 2021-35211.
This is a perfect example of a modern, practical ROP chain in action.
What were they trying to do?
Their ultimate goal, as is so often the case with ROP on modern systems, was to bypass that strict library policy we discussed earlier, DEP, or Data Execution Prevention.
Right, because if you can turn off the WX alarm system, you don't need to rely on the limited, agonizingly constrained gadgets anymore. You can just run your own custom-written shellcode.
Exactly. The ROP chain isn't the final weapon. It's just the lockpick to open the door.
That's a great way to look at it.
In the Windows operating system, there's a powerful system function called virtual protect. In Linux, there's a very similar function called improtect.
And what do these functions do?
These functions possess the administrative power to change the rules of the library on the fly. They can take a specific section of memory, like the very stack where the attacker has hidden their long username and shellcode, and alter its permissions from read-write to read-write-execute.
Turning the scratch pad back into a rulebook.
Exactly. But the operating system doesn't just let anyone call virtual protect blindly. The function requires strict parameters.
Like filling out a form.
It needs to be told exactly which memory address to change, how large the area of memory is, what the new permissions should be, and a place to save the old permissions.
It needs arguments.
In a 64-bit Windows program, the rules for passing these arguments, the calling convention, dictate that the first 4 parameters must be placed into 4 very specific processor registers before the function is called.
And those are?
RCX, RAP, RE8, and R9.
So the attacker's ROP chain has to juggle values perfectly into those 4 tiny slots.
It is a remarkably delicate choreography. The attacker must find a gadget that pops a value off the stack and puts it into RCX, then another gadget to pop the size into RDX, and so on.
Just moving the pieces around.
In the Bishop Fox exploit documentation, the researcher notes spending hours just trying to find a way to place a specific value into that 4th register, R9.
Wait, really? They couldn't just find a simple pop into R9 and return gadget?
They could not. The specific library they were working with didn't contain that exact sequence of letters without also containing bad character.
Oh, because of the null bytes or other filters?
Yes. They eventually had to settle for a complex multi-gadget chain. They found a gadget to pop the value into a different register, RAX first, and then found another gadget to move the value from RAX into R9.
A completely roundabout way to do it.
This compromise consumed extra space on the stack and required perfectly aligning the stack pointer between steps. It highlights the deeply constrained, puzzle-solving nature of this work.
A puzzle where the pieces are microscopic, scattered in the dark, and the rules are completely unforgiving.
Beautifully put.
And speaking of space on the stack, That constraint leads us beautifully into the next phase of our journey. Sometimes the scratch pad just isn't physically big enough to hold the entire ransom note.
It happens quite often.
This introduces us to the graceful spatial gymnastics known as stack pivoting.
As we've established, the ROP chain lives on the stack, and the stack pointer, like our typewriter carriage, guides the execution down that list.
Right.
But in many real-world vulnerabilities, the initial buffer overflow might only allow the attacker to overwrite a few dozen bytes of the stack before hitting a boundary or causing a crash.
That might be enough room for 2 or 3 gadget addresses, but a full chain to perfectly align registers and call virtual protect might require hundreds of bytes.
Exactly. It is a severe spatial limitation.
You broke it into the library, but you only have a single tiny post-it note to write your entire set of instructions on.
To solve this, attackers utilize a completely different region of memory. If the stack is the organized scratch pad, there is another area called the heap.
The heap.
The heap is a massive, sprawling expanse of memory used by the program for dynamic, large-scale storage, like loading a high-resolution image or a large database file.
Why is the attacker allowed to put things there?
Attackers can often manipulate the program's normal behavior to allocate memory on the heap. For example, by sending a large string of data disguised as an image file or a complex network packet.
Oh, I see.
This technique is appropriately named a heap spray. They fill this massive expanse of the heap with thousands upon thousands of copies of their long, complete ROP chain, ensuring it is sitting out there safely stored in memory, waiting in the dark.
But there is a fundamental disconnect here. The massive payload is sitting out in the heap, but the CPU's stack pointer, our typewriter carriage, is still looking at the tiny original stack where the initial overflow happened.
Right.
How do they bridge that gap?
The attacker bridges the gap using a very specific, highly prized type of gadget called a stat pivot.
A stat pivot.
Instead of doing arithmetic or moving data between general registers, a stack pivot forcefully modifies the stack pointer register itself.
Walk us through the mechanics of a pivot. What does the instruction look like?
A common example is the assembly instruction X2T AS.
Exchange ESP and E6.
Exactly. This exchange instruction takes whatever memory address is currently held in the EX register and completely swaps it with the value in the stack pointer, %SPU.
So the attacker uses their tiny post-it note on the original stack to run just 1 or 2 setup gadgets. These setup gadgets calculate the address of the massive payload out in the heap and place that address into the EX register.
Then they call it the stack pivot gadget. With one swift silicon-level motion, the instruction grabs the CPU's attention, rips the stack pointer away from the designated stack, and points it directly into the vast expanse of the heap.
And the CPU, obedient as always, doesn't question why its scratch pad has suddenly relocated to a completely different zip code in memory.
Not for a second.
It just says, okay, this is the stack now, looks at the new location, sees the first address of the massive ROP chain, and the carriage return continues pulling gadgets seamlessly. It is an astonishing sleight of hand.
It is a profound violation of the program's spatial integrity. The CPU is completely blind to context.
Wow.
And this exact maneuver, the geographical relocation of the stack pointer, is what inspired a fascinating defense mechanism developed by researchers at Binghamton and Syracuse universities, detailed in the sources as P-blocker.
So, what does this all mean? How does P-blocker actually stop this sleight of hand?
The researchers observed a fundamental architectural truth. Under normal, healthy operation, the stack pointer should always, without exception, be pointing to the actual memory region, officially assigned as the stack by the operating system.
Right.
It should never spontaneously point out into the heap. They defined this boundary as the stack localization property.
A clear boundary line drawn in the sand of memory.
P-blocker enforces this boundary by operating at the compiler level. When the software developer is compiling their program from source code into a binary executable, the P-blocker compiler quietly inserts tiny microscopic security checks right before every single return instruction.
What exactly is the check asking?
It asks a simple mathematical question. Is the current value of the stack pointer numerically between the starting address and the ending address of the designated stack?
Ah, so simple.
When the attacker triggers their stack pivot and throws the pointer out into the heap, the very next read instruction is intercepted by P-blocker. The check fails. P-blocker detects this sanity failure and immediately halts the entire program, neutralizing the ROP attack in its tracks before the chain can even begin.
That is a brilliant shift in defensive thinking. Defenders stopped looking solely at what the computer was executing because the WX policy proved that wasn't enough. They started paying very close attention to where the CPU was looking when it executed it.
The geometry and geography of memory became the new battleground.
Before we move deeper into this labyrinth, let's take a gentle pause. Allow the intricate mechanics of the stack pointer, the hidden letters of the gadgets, and the spatial gymnastics of the pivot to settle in your mind.
It is a lot to take in, but it's deeply logical.
We are currently decoding the dark channel of software exploitation, exploring a hidden world of elegance and vulnerability. If you are finding peace and understanding in this deep dive, I warmly invite you again to leave a like and subscribe to support our continued soothing journeys into the complex heart of technology.
As we resume our descent, we must recognize that the cat-and-mouse game between attackers and defenders is a rhythm of constant escalating adaptation.
It never stops.
As defenses like P-blocker and DEP grew more robust, defenders realized they needed to attack the core assumption of the ROP technique itself.
Which is?
If return-oriented programming relies entirely on knowing exactly where the gadgets are located in the library's memory, what happens if we simply take away the attacker's map?
A strategy of confusion. Enter address space layout randomization, universally known as ASLR.
ASLR was a monumental shift in operating system design. To understand its impact, look at how memory worked before it.
Okay, let's visualize that.
Before ASLR, an essential library like lib would be loaded into the exact same memory coordinates every single time a computer booted up. If a useful POP2X gadget was located at the hexadecimal address 0x08048,000 on the attacker's machine in their lab,
They knew with absolute certainty it would be at that exact same address on your machine. The ransom note could be pre-written in advance, photocopied, and mailed out to millions of computers, and it would work on all of them.
But with ASLR, the operating system introduces entropy. It scrambles the locations of everything.
Everything.
The stack, the heap, the executable libraries, they are all mapped to secret pseudo-random coordinates in the vast ocean of memory every single time a program launches.
The islands of code are constantly moving.
Yes.
If the attacker doesn't know where the library was placed today, their hard-coded gadget addresses point to empty, dark space. The typewriter carriage slides over, strikes the paper, and hits absolutely nothing.
The program simply crashes, the alarm bells ring, and the attack fails completely. If we connect this to the bigger picture, we see attackers getting incredibly, almost frighteningly creative in response. They realized that to defeat randomization, they didn't need to break the underlying mathematics of the entropy.
They didn't have to predict the randomness.
No, they just needed to find a leak, a tiny crack in the hull of the ship. This realization birthed a technique known as JIT-ROP, or just-in-time ROP.
Just the name implies a sense of breathless speed, but happening in complete microscopic silence. How does it work?
JIT-ROP relies on chaining two different vulnerabilities together. First, the attacker needs a memory disclosure vulnerability,
A leak?
a flaw that allows them to peek at just a single piece of data inside the victim's randomized memory. Perhaps the program accidentally prints out a pointer or allows the attacker to read slightly past the bounds of an array.
So they find one single coordinate, but how does one coordinate reveal the whole map?
They use that single leaked pointer to locate one single page of executable code in memory. Then the automation takes over.
Oh, wow.
In a fraction of a millisecond, the attacker's exploit script dynamically reads that single page of memory, disassembles the raw bytes back into readable by 86 assembly instructions on the fly, and analyzes it.
They are reading the book while the book is falling through the air.
Exactly. Inside that first page of code, they find references, calls, or jumps that point to other moving islands of code. They follow those references, mapping out a second page, then a third.
Expanding their vision?
They recursively map the memory space, find the specific gadgets they need on those newly discovered pages, and compile a brand new, custom-tailored ROP chain right there in the target's memory, just in time to execute it before the program can close.
It is like a submarine in the fog, seeing the faint glow of a single lighthouse, and using that single point of reference to instantly calculate the position of the entire coastline, build a torpedo perfectly shaped for that coastline, and fire it. All happening in the blink of an eye.
That's a beautiful way to see it. And then there is an even more patient, methodical approach used when there is no lighthouse at all. This is called blind ROP, or BROP, developed by researchers at Stanford.
Blind ROP.
This technique specifically targets internet-facing servers like Apache or Nginx web servers running on Linux.
What makes a web server so vulnerable to a blind attack?
Web servers are designed for maximum resilience. If a server receives a malformed request and the process handling it crashes, the main server doesn't shut down. It automatically restarts it,
Okay, to keep the site online.
creating a fresh new child process to handle the next request, ensuring the website stays online.
A self-healing system. But attackers turn that healing against itself.
They did. They leveraged a deeply ingrained behavior in how Linux creates these child processes, specifically using the fork system call. When a parent process forks a child, the child inherits an exact bit-for-bit duplicate of the parent's memory layout.
Oh, wait, so the deck of cards is shuffled once when the server boots up, but every single child process gets dealt the exact same hand of cards.
Precisely. The ASLR entropy is static across crashes. The attacker connects to the web server and initiates a buffer overflow, probing just one single byte of the return address. They guess a value.
And if they guess wrong.
If they guess a value wrong, the return address is corrupted, the child process crashes, and the network connection drops.
Silence. A miss. The attacker knows they guessed incorrectly.
But the parent server instantly spins up a fresh, identical child. The attacker reconnects and tries the next possible byte value. Because a single byte only has 256 possible values, they only have to make a maximum of 256 guesses before they find the correct one.
And when they finally get it right.
When they finally guess the correct byte, the program doesn't crash, it continues running normally. The attacker sees the connection stay open, and they know, with absolute certainty, they have correctly mapped one single byte of the randomized layout.
It is like a submarine using active sonar in pitch black water. Ping, silence, ping, silence, ping, and echo.
Exactly.
They map the first byte, and move to the second, then the third. By systematically crashing the server thousands of times over a few minutes, they effectively map the entire 64-bit randomized memory space completely blind, relying entirely on the binary feedback of a crash or continuation. The persistence, the mathematics of it is astounding.
It's an incredibly patient attack, but as defenders watched these intricate maps being drawn in the dark, they noticed something else.
What was that?
They realized that a traditional ROP attack, no matter how perfectly crafted, leaves a very distinct, unavoidable fingerprint on the processor's behavior. This transitions us to the next era of our deep dive, post-ROP evolutions, or life without returns.
Life without returns.
Defenders, observing the mechanics of ROP, realize that a normal, healthy program executes a relatively balanced ratio of call instructions to read instructions. You call a function, you go do the work, you return from it, it breathes in, it breathes out.
But a ROP chain doesn't breathe normally.
No. ROP chain is a severe, unnatural spike of continuous read instructions, firing one after other in rapid succession without any corresponding call instructions. Furthermore, modern processors and operating systems began monitoring the call stack's last in, first out integrity.
How does that work?
They maintain a hidden shadow stack. If a return address doesn't perfectly match a previous call made by the program, the hardware alarm goes off.
The typewriter carriage is returning too fast, too often, without ever typing any actual words on the page. The mechanical rhythm of the machine is broken, and the defenders learn to listen for that broken rhythm.
So the security researchers Stephen Chekaway and Hovav Shacham asked a deeply theoretical question. Is the read instruction actually necessary to build a ransom note?
And I'm guessing the answer was no.
The answer was no. They demonstrated a paradigm called ROP without returns. They proved mathematically that attackers could drop the read instruction entirely and still maintain Turing completeness.
Wait, I am struggling to visualize this. The entire mechanism we've discussed, the carriage return sliding the attention down the stack to the next address, relies on read.
Yes, it does.
If you take away the carriage return, how do you advance the page? How do you move from one gadget to the next?
By finding a new mechanical sequence, they scoured the libraries and utilized what they called update load branch sequences.
Update load branch?
Instead of relying on ret to pop the stack and jump simultaneously, they found gadgets that separate those actions. They used the standard pop instruction to load a value from the stack into a general purpose register, like edX.
Okay.
And then they end the gadget with an indirect jump instruction, like jump edX, which transfers control to the address now held in that register.
It achieves the exact same flow of control, pulling the next address and jumping to it, but it completely sidesteps the hardware monitors because technically no ret instructions are ever executed.
So not at all.
It is a ghost slipping through the perimeter fence because the guards are exclusively looking for people climbing over the main gate.
And this philosophy of abandoning the return instruction evolved into something even more architecturally bizarre and sophisticated. Jump-oriented programming, or JOP.
Let's explore JOP. If ROP is a typewriter on a stack, what is JOP?
Jump-oriented programming is a masterpiece of subversion. In traditional ROP, the stack acts as the physical conveyor belt for the payload, and the stack pointer moves along it. JOP abandons the stack entirely for its control flow. Instead, it relies on a very specific, carefully chosen snippet of code called a dispatcher gadget.
Let's visualize this dispatcher gadget. I picture it like a switch operator sitting in a central tower of a massive train yard, or perhaps an internal continuous loop spinning inside the memory.
The central tower is a remarkably accurate analogy. In JOP, the attacker creates a dispatch table somewhere in memory, a simple, flat list of gadget addresses.
Okay.
The dispatcher gadget's entire job is to consult this table, read the first address, advance its own internal pointer to the next entry in the table, and execute a jump to that first functional gadget.
So the dispatcher sends the train down a track to a functional gadget. Let's say a gadget that adds two numbers together to prepare a virtual protect argument.
Exactly.
But remember, in JOP, there are no return instructions. When the train reaches the end of the track, how does it get back to the central yard to get its next destination?
That is the defining brilliant constraint of JOP. Every single functional gadget used in a JOP attack must end with an indirect jump that points explicitly back to the dispatcher gadget.
Oh, wow.
It forms a perfect closed loop. The dispatcher reads the table, jumps out to the gadget performs its math, and jumps right back to the dispatcher. The dispatcher reads the next table entry, jumps to the next gadget, and the cycle continues indefinitely.
This sounds like the attacker is no longer just chaining fragmented instructions. They're literally building a virtual machine with its own fetching and decoding cycle, running entirely inside the victim's memory, using the victim's own fragments of code to power it. Is that accurate?
It is exactly accurate. They have synthesized a brand new, hostile processor architecture within the software itself. The dispatch table is the new program. The dispatcher is the new CPU core.
That is chilling.
And the evolution of control flow subversion doesn't stop there. As defenses continued to probe these loops, researchers discovered other avenues that abandon assembly-level gadgets entirely.
What could be higher level than assembly gadgets?
Consider SIG-return-oriented programming, or SROP. This technique abuses the UNEX signal handling mechanism.
How does a signal work in UNAX?
When you press Ctrl plus C in a terminal, you are sending a signal to the program to interrupt it. When the Linux kernel delivers a signal to a process, it has to pause what the program is doing.
Like freezing time.
Yes. To ensure the program can resume safely later, the kernel takes the current state of every single register in the CPU and saves them all to the stack in a massive structured block called a SIG context frame.
It takes a complete snapshot of the CPU's brain and saves it on the scratchpad.
Exactly. And when the program is done handling the signal, it calls a special system function called SIG-return. This function reads that SIG context frame from the stack and instantly restores all the registers, loading them back into the CPU en masse.
I see where this is going. If the attacker can forge their own massive SIG context frame on the stack, filling it with exactly the values they want in every single register,
and then force the program to call SIG-return. The kernel will read the attacker's fake frame and instantly load every single register with the attacker's data in one fell swoop.
no need for complex ROP chains to juggle values between racks and R9.
No juggling needed.
SROP sets the entire CPU state in a single devastating action.
It is breathtaking. And I saw another acronym in our sources. COOKIE, Counterfeit Object-Oriented Programming.
That sounds like high-level forgery.
It is semantic forgery.
Yeah.
COOKIE specifically targets complex applications written in object-oriented languages like C++ Air, such as modern web browsers.
Okay, how does that work?
In C++ Air, objects use a feature called polymorphism, implemented via vtables, which are arrays of pointers to the object's virtual functions.
So instead of a list of tiny assembly gadgets, a vtable is a list of pointers to entire complex C++ functions.
Yes. Instead of chaining tiny assembly instructions, COOKIE hijacks these complex, pre-existing virtual functions. The attacker forges counterfeit objects in memory, points their vtable pointers to a fake vtable they control, and fills that fake vtable with pointers to existing legitimate C++ functions scattered throughout the program.
They weave a path through the highest level of the application's logic.
They loop through arrays of these counterfeit objects, chaining together entire functions to perform malicious actions. It is a high-level semantic code reuse attack that doesn't rely on stack pivots or corrupted instruction pointers in the traditional sense, making it incredibly difficult for standard low-level defenses to detect.
We are drifting from the microscopic mechanics of the stack pointer into the overarching philosophy of computer security. The sheer scale and creativity of these techniques are staggering.
It's a vast landscape.
Which brings us to our final overarching theme, the endless horizon of control flow integrity.
To understand the sheer scope of the problem ROP created, consider a security report published by Microsoft. They analyzed exploits actively targeting their software products in the wild and found that over 90% of them utilized ROP or similar code reuse techniques.
90%, wow.
It wasn't just a theoretical academic exercise, it became the absolute standard for binary exploitation worldwide. The entire technology industry had to respond.
The walls of the library were breached, the guards were confused by the virtual machines, so they had to reinforce the very foundation of the building itself.
Exactly. This led to the development of broad, sweeping strategies collectively known as control flow integrity, or CFI.
What is the goal of CFI?
The philosophical goal of CFI is ambitious: to map out every single valid, intended path that a program can theoretically take before it ever runs.
To draw a perfect map of the city before anyone is allowed to drive in it.
Yes. Then, during execution, the hardware-software constantly checks every single indirect jump and return. Is this jump to a gadget a valid intended path on our pre-proved map?
And if it's not?
If the answer is no, the program terminates immediately. Modern processors now include hardware-level mitigations like Intel CET, or control flow enforcement technology.
How does Intel CET work at the silicon level?
Intel CET implements that shadow stack we mentioned earlier, but it does it directly in the hardware. When a call instruction is executed, the return address is pushed to the normal stack, but CET also pushes it to a hidden, hardware-protected shadow stack that the attacker cannot overwrite.
Okay, so it has a backup copy.
Exactly. When the reach instruction executes, the processor compares the address on the normal stack to the address on the shadow stack. If they don't match exactly, a hardware exception is raised, instantly killing the ROP attack.
It sounds foolproof. If you know the map and you have an untouchable shadow stack checking the math, you can catch anyone going off-road.
This raises an important question regarding the limitations of these complex defenses. Creating a perfectly strict, fine-grained map of every possible path in a massive modern program, like a web browser with tens of millions of lines of code, is computationally heavy and incredibly complex.
The map would be so detailed it would slow down the city's traffic to a crawl.
Precisely. To make CFI practical and fast enough for daily use on consumer laptops, defenders often have to implement coarse-grained CFI.
Coarse-grained?
This means the map isn't perfect. It groups certain paths together. It says any function that takes two integers as arguments can validly jump to any other function that takes two integers.
A map with much lower resolution.
Yes, and attackers, with their boundless patience, found that within that lower resolution, within those grouped permissible paths, there was still just enough wiggle room to construct specialized ROP and JOP chains.
Of course they did.
Furthermore, researchers demonstrated opaque CFI bypasses. They showed that if an attacker can leverage an implementation disclosure, a memory leak that reveals the underlying rules and layout of the CFI map itself, they can carefully weave their chains through the permitted legal pathways.
They turn the defense's own map against it, hiding in plain sight.
It is a breathtaking dance. An endless cycle of a wall being built and a new, more elaborate ladder being forged in the dark.
As we gently drift back up to the surface after this incredibly deep technical dive, let us take a moment to reflect on the landscape we've traversed together.
We covered a lot of ground today.
We really did. We have seen how a simple, elegant rule like WX, designed to protect the library of memory, gave birth to an entirely new art form of exploitation.
The ransom note.
We witnessed the attacker as a meticulous kidnapper, cutting hidden letters from the vast ocean of lib, using the obedient stack pointer as a typewriter carriage to write a silent, devastating ransom note.
We saw the geometry of memory manipulated through stack pivots.
Yes, and the dark oceans navigated by the blind sonar of ROP and the creation of phantom virtual machines through jump-oriented programming. There is an undeniable dark elegance to code reuse attacks, a mathematical beauty even in their malicious intent.
It's engineering pushed to its absolute limits.
But it leaves us with a lingering, provocative thought to ponder in the quiet moments after we part ways. We have seen hardware manufacturers and software developers add incredibly complex, heavy layers of security over the decades, DEP, ASLR, P-blocker, CFI, shadow stacks baked directly into silicon just to stop the computer from turning its own authorized code against itself.
Constantly patching the ship.
One must step back and ask, are we simply putting ever more elaborate band-aids on an architecture that is fundamentally flawed?
That's the real question, isn't it?
If a system requires this much continuous exhaustive patching, this much overhead just to maintain basic sanity and spatial integrity, does the fundamental von Neumann architecture of modern computing, the very idea that data and instructions reside in the same memory space, need to be abandoned entirely?
It might be the only way to true security.
Will we eventually reach a horizon where we must redesign the central processing unit from the ground up, enforcing absolute memory safety at the very core of its physical physics, rather than trying to constantly police the dark channels after the fact?
It's a profound thought.
It is something heavy yet fascinating to mull over as you go about your day. It has been a true pleasure decoding the dark channel with you today. We hope you found this deep dive as soothing as it was illuminating, and that the mechanics of memory now feel a little less mysterious.
Thank you for joining us in the Quiet Room.
Please warmly consider leaving a like and subscribing so we may continue to share these quiet journeys into the depths of technology with you. Until next time, take care.